In Chapter 13, Section 2, we will look at calculus of vectors. So we're going to do more vector work, looking at their derivatives and their curvature and all sorts of stuff. Okay, so it says consider the following vector equation. R of t equals 2t minus 5 and t squared plus 4. So when t is 0, you get the point -5 and 4. And so we get a point. I'm just going to work from the answer here. This is when t is 0. And you can see when t is 0, you get -5 and 4. So we have the point -5, 4. And then you can plug in other t values, and you'll see that it looks like this parabola here in the black. That is the vector function. Now the derivative of the vector function would be pretty straightforward. You just have to take the derivative of each of these component functions. So t squared plus 4. So we have to lean back on our calculus 1 derivatives, and the derivative of a constant in front of a variable is just the constant. The derivative of a constant without a variable on it is 0, so the -5 goes away. The derivative of a variable with a power is you bring the power down and then you subtract 1 from the power. And then the derivative of a constant like plus 4 is 0. So the derivative of this function is 2, 2t, right there. And the way that shows up is when t is 0, you get the derivative function is going to be 2, 0. So it's 2 in the x, 0 in the y. And basically, derivatives are lines that are tangent to the curve. So this is a horizontal line, x equal to, that has a distance of 2. So this, when t is 0, this would be the derivative line. So it's tangent to that. Then when t is 1, you're going to get 2, plug in 1 for t there, and you're going to get 2 again. So that's, I believe that's this one right here. It's 2 in the x, 2 in the y. 2 in the x, 2 in the y. That's this tangent line. And then when t is 2, the derivative is going to be 2, 4. And so we're up here. Notice how this is getting sharper and sharper. It's 2 over and 4 up. And so that's how your vector derivative of the vector equation is going to look. It's going to be these tangent lines that grow along this black parabola. Okay, so that's problem 1. Okay, problem 2. Find the derivative of r of t. So we have a pretty big vector equation here. It's a times t times cosine of 3t in the I direction. And it's, I'm writing it in vector form, that's fine. Then they have b sine to the 5th power of t in the j direction, and then they have c times cosine to the 4th power of t in the k direction. So there's your vector, and basically we're just going to do this derivative one chunk at a time. So let's start with this one. So what they'll often do is say this is f of t, this one's g of t, and this one's h of t. So we can ignore the I, j, and k aspect of it and just look at the function in front of I and the function in front of j, and the function in front of k. So let's just look at that. Let's say I have the function at cosine 3t. That's it. The derivative of this function is going to be, so this is what we call product rule. At is its own function times cosine of 3t, which is its own function. So we have to make this into two separate functions, and we're going to call the first function f and the second function g. And product rule says the derivative of two functions being multiplied is fig plus gif. So fig plus gif. Where I'm saying fig is f prime. So f prime looks like an I kind of, so fig plus gif g prime. But what is little f prime? So if little f is at and little g is cosine 3t, so notice I'm just breaking that two functions multiplied into their own functions. F prime is very simple, it's just a. So the t goes away in the derivative and you're left with the letter in front. Now g prime is a little more intense. First you have to think, what's the derivative of cosine? The derivative of cosine is negative sine. And whatever the argument is, you leave it the same. So if it's cosine 3t, it's sine of 3t. But, boy, there's a lot of review on this one. That's the derivative of the outside. Then we have to do the derivative of the inside, which would be the derivative of 3t. So this whole thing is times the derivative of 3t, which is 3. And that's called chain rule. So we just reviewed product rule and chain rule. So it's not enough to just call this minus sine 3t. You have to also take the derivative of the inside function, 3 times t, which is just 3. Okay, so this is going to simplify to minus, you can write the 3 in front, minus 3 sine of 3t. Okay, now we have to put these four things into this fig plus gif up here. So f prime was a times the original g, which was cosine 3t, plus g prime, which is negative 3 sine of 3t, times the original f, which was at. So the first function, its derivative is, if I simplify a little bit, a cosine of 3t minus 3at sine 3t. And you can see I wrote that in front of the I vector. So a cosine 3t minus 3at sine 3t. So all of that goes in front of the I component, unit vector. That's one of three derivatives we need to do. Okay, the other 200 is bad though, because you don't need product rule. So let's look at the other two derivatives. So now we are going to use g of t and h of t. So we have g of t g of t, whatever's in front of the j component, was b sine 5 of t. Okay, and to do this derivative, we have to use chain rule again. So I have to take the derivative of the outside. The derivative of the outside just says bring the 5 down and subtract 1 from the 5. So we're going to get 5b sine, subtract 1 from 5 and get 4 of t. Times, now I have to do the derivative of the inside. So the derivative of the inside function is just sine of t. So the derivative of sine is cosine, so this would be cosine of t. And if we write this, we'll just kind of push these together and we'll get 5b sine 4t cosine t. And that should be right here. So you can see in front of the j term, we have that 5b sine t to the 4th times cosine t. Okay, last one. h of t. So this is a nice review of derivatives of trig functions and product rule, chain rule, all those things we learned in Calculus 1. Can't just forget them. H of t is the letter c times cosine raised to the fourth of t. This one's going to be really similar. First, the derivative of the outside is going to be, bring the 4 out front, so it's 4c cosine, subtract 1, 3t, times derivative of the inside, the derivative of the inside would not include the c or the 4. It's just cosine t. The derivative of cosine is negative sine t. So putting this together, we would bring the minus out front, so we get minus 4c cosine 3t times sine t. And we should have that there, so the minus, the 4, the c, minus 4c cosine t to the third times sine t, and that's all in front of k. So notice you do have to write this in vector notation, so you have to use I, J, and K, which you can get from the Tools menu. When you click in this box, it'll show Tools on the right, click Vectors, and select the I, J, and K letters to put those in. Okay, it looks like a lot of work, but it is just derivatives that, believe it or not, you should have seen before at some point. Okay, let's look at 3. I believe 3 is going to be very similar. So we've got not quite. It says find the unit tangent vector t of capital T of t, so that's the tangent vector, unit tangent vector, at the point with the given value of the parameter t. So we have r of t, the vector function in parametric form is 4t e to the negative t, comma, 8 times the arctangent of t, comma, 8 e to the t. Okay, and to do the unit tangent vector, we need to have the equation that looks like this. Let's see here. Tangent vector as a function of t is, it is the derivative of the vector equation divided by the magnitude of the derivative of the vector equation. And it turns out to be nicer if we're given a point. So it says at t equals 0. So if time is 0, then this simplifies to the derivative where you let time equal 0 divided by the magnitude of the derivative where you let time, or the parameter t, usually is time, equal to 0. So we just have to find the derivative of this again. So let's look at this. R prime of t is going to equal, now this is two equations being multiplied, so you do have to use product rule, but I'm going to go a little quicker this time with it. So the product rule also just basically says take the derivative of the first, so 4t would be 4, times the second left alone, plus the first left alone, 4 times t, times the derivative of the second. Now the derivative of e to the minus t would be minus e to the minus t. Okay, so that is the, all of that is the I term. Let me not write i's and j's and all that. Let me just write it in vector form. So let's call this just the vector. That's the first component. Okay, now this one. Now this one is a little tricky. We have to maybe look up that the derivative with respect to t of arctangent is equal to 1 over 1 plus t squared. So you would have proven that in Calculus 2, where we introduced derivatives of arc trig functions, and you can remember that. Now the 8 in front is just going to be along for the ride, so this is actually going to be 8. We'll multiply it into the numerator, so it's going to be 8 over 1 plus t squared. Okay, then the last term, the derivative, and I kind of did this in this last one without too much fanfare, the derivative with respect to t of e raised to any number times t is just a times e to the at. So like when a was minus 1, like in that second part of this first coordinate, if I have e to the minus 1t, then by this pattern, the minus 1 comes down, and it's just e to the minus 1t. So one thing about derivatives of e is that the original function is always there. It's always going to stick around. So if I have the derivative of 8et, it's just 8et. So the 8 sticks around for the ride, and the derivative of et is et, so that stays the same. Okay, that is the derivative function. Now, luckily for us, we just have to plug in 0 for this stuff. So the derivative when t is 0 is going to be 4 e to the 0 plus 4 times 0 times negative e to the 0. There is no negative 0, so I don't have to worry about that negative exponent. This one's going to be 8 over 1 plus 0 squared, and this one's going to be 8e to the 0. Well, e to the 0 is 1. Anything to the 0 power is 1. So this is going to be 4 times 1, which is 4. This 0 is going to kill off all the rest of the stuff, so this whole thing just becomes 4. This is just going to be 8 over 1, which is 8, and this is going to be 8 times 1, which is 8. So that is the vector equation when t is equal to 0. Now that's going to be the numerator. So this whole thing is going to go on top. Now we need the magnitude of this vector. Well, the magnitude of a vector is just the square root of its components squared added together. And if you add up all those numbers, you're going to get the square root of 144, yeah, 144, which is 12. So putting it all together, the tangent unit vector at 0 is the vector, the derivative of the vector when t is 0, which was 488, divided by the magnitude of that vector, which is 12. And you can divide a scalar into a vector. Just take each thing divided by 12. And that does simplify to 1/3, 2/3, and 2/3, which I have written right there. 1/3, 2/3, and 2/3. Divide everything by 4. Okay, and that'll be problem 3, tangent unit vector. Okay, 4, find the unit tangent vector t of t at the point with the given value of the parameter t. So t is 1 this time. So they have us with the vector equal to 6t to the 1/2 power in the I direction plus 3t squared in the j direction plus 2t in the k direction. Now the derivative of this one, not so bad. We don't have to do any kind of product rule or anything like that. T to the 1/2, bring the 1/2 down. So 6 times 1/2 is 3. Subtract 1 from this exponent, so it's going to be minus 1/2. That's in the I direction. The derivative of 3t squared is bring the 2 down into the 3, doubles it into 6, and then subtract 1 from 2, it becomes t to the 1st power in the j direction. and then plus the derivative of 2t would just be 2 in the k direction. Now they want us to plug in 1 for the parameter. So t to the minus 1/2 is just, so it's going to be 1 to the minus 1/2, but 1 to the anything is 1. This is going to be plus 6 times 1 in the j, and then 2 in the k. So we're going to get 3, 6, 2. That is the derivative of the vector equation when the parameter t is 1. Now, to calculate the tangent unit vector, we need the magnitude of this vector at 1, which is just the square root of the component squared, 3 squared plus 6 squared plus 2 squared. They give you nice numbers in this one, square root of 49, which is 7. So the tangent unit vector, oh, I got to be careful. This is only true for the point when t is 1. So I can't write t, I have to write 1 there, is this vector at 1 divided by the magnitude of the vector, derivative vector, at 1. So we get 3, 6, 2 divided by 7, which is just going to be 3/7, 6/7, 2/7. And that's what I have there. Okay, so that would be another example of this approach in problem 4. Problem 5. Evaluate the integral. So this is a brand new type of problem. It's different than the ones we just did. And basically you're just going to do the integral applied to both of these equations. So we have the integral from 0 to 1 of 2 over 1 plus t squared dt, and that's going to be the j component. And then we have plus the integral 0 to 1 4t cubed over 1 plus t to the 4th dt in the k direction. Well, we just saw this one. So if I bring this 2 out front, this is 2 integral 0 to 1, 1 over 1 plus t squared dt. Well, we said the derivative of arctangent was this right here, 1 over 1 plus t squared. So this whole thing is just going to become 2 arctangent of t evaluated from 0 to 1. So this whole antiderivative just becomes arctangent. And then 0 to 1 for our limits of integration, and a 2 is there for the ride. Okay, so we're going to get 2 arctangent of 1 minus arctangent of 0. And arctangent of 1 is, in radians, arctangent of 1 is pi over 2. Pi over 4. Minus arctangent of 0 is 0. So this is all going to equal 2 pi over 4, which is the same as pi over 2. So the integral in the j direction is pi over 2. Okay, so that's half of it. Now we have to do this second half. Let me see if color can help us here. So this part in front of the k. So let's do this down here. 4t cubed over 1 plus t to the 4th dt. Okay, this we have to use something called u substitution. So you might recognize that the derivative of t to the 4th is 4t to the 3rd. So if you have if you see a derivative of a function in the same antiderivative, then you're basically guaranteed to be able to use u substitution. So we're going to let u equal 1 plus t to the 4th. Then the derivative of that function would be 4t to the 3rd times dt. Okay, so this is the only thing that might feel a little strange in u substitution is normally if I see the equation 1 plus t to the fourth, I would say the derivative is just 1 goes away, becomes 0. The derivative of t to the fourth is bring the 4 down, subtract 1, so it's 4t3. But we add dt here because we're playing with different variables. So we're playing with u and t. This dt tells me, hey, I just did a derivative where t is the variable. So think of it as like a naming convention. I'm naming the fact that t is the variable I'm using in my derivative rules. But now we're going to solve for that dt. So to solve for that dt, we're going to divide by 4t cubed from both sides. And on the right side, it's going to cancel. So we're going to get du over 4t cubed equals dt. Now we go back to this original integral and we change anything that we can. So it's still the integral 0 to 1. 4t cubed I can't change, so it's still 4t cubed. But the bottom, 1 plus t to the fourth, I can change that to u. Because that's, I said u should be 1 plus t4. And dt I'm going to change to du divided by 4t cubed. And these are being multiplied. So this is a sticking point. Sometimes students don't understand this. This dt I'm replacing with this dt, which is really all of this. So that's how that appeared there. And this should always happen if you've done this right. The t's are all going to go away. So 4t cubed on top, 4t cubed on bottom, and you're going to get the antiderivative will become the integral from 0 to 1 of du over u. And you might recall from calculus that if you have the antiderivative of the derivative of x over x, this is the natural log of x. So this whole thing is going to become the natural log of u from 0 to 1. Now some people will have you change those limits of integration. I'm not going to. I'm going to do what's called back substitution. So I'm going to say that u is actually 1 plus t to the fourth. And then I can keep these limits 0 to 1 the exact same. So I'm replacing u with what it was from the beginning. Okay, now we plug in 1 and we get the natural log of 1 plus 1 to the fourth minus plug in 0 would be the natural log of 1 plus 0 to the fourth. This is just going to equal natural log of 2. And minus, this is the natural log of 1. Now you can try this on your calculators. Type natural log of 1. That is going to equal 0. So this whole thing is just going to simplify to the natural log of 2 in the k direction. So the final answer is putting those two things together. Color, I need color here. You're going to say we've got natural log of 2 in the k direction, pi over 2 in the j direction, and those show up right here. Pi over 2 in the j plus natural log of 2 in the k direction. Okay, so we can take derivatives of vector equations, we can take antiderivatives of vector equations, and we're using all those rules we learned from Calculus 1, Calculus 2, use substitution, natural logs, arctangents, all these different tools. Case 6 is going to be no different, although I think it's a little easier to do because it's just polynomial. So we have the antiderivative from 0 to 1 again of 8t cubed in the I minus 15t squared in the j plus 10t to the fourth in the k. And we just have to remember how to do the antiderivative. So the antiderivative says leave constants alone, add 1 to the power, and divide by the same number. So derivatives bring the power down and subtract 1 from the power. Antiderivatives add 1 to the power and then divide by that same number. So t3 becomes t4 over 4. and there's an I there. And we're doing this from 0 to 1. So don't forget your limits of integration. Minus 15 sticks around. T2 becomes T3 over 3. So add 1 and divide by the same number, and that's from 0 to 1 in the j direction. 10 sticks around for the ride. T4 becomes T5 over 5, 0 to 1 in the k direction. So 8 over 4 is 2, so this is going to be 2, and it's going to be t to the 4th from 0 to 1 in the I. 15 divided by 3 is going to be minus 5 t to the 3rd from 0 to 1 in the j. 10 divided by 5 is 2 t to the 5th, 0 to 1 in the k. So we're going to get 2, 1 to the 4th minus 0 to the 4th in the I, minus 5 times 1 to the 3rd minus 0 to the 3rd in the j. Just putting in the limits of integration now, top minus bottom, plus 2 times 1 to the 5th minus 0 to the 5th in the k. Well, all those zeros are going to drop out. All these ones aren't going to change anything. So we just get 2i minus 5j plus 2k. And 2i minus 5j plus 2k, yep, that's exactly right. Okay, so just recalling antiderivative rule for powers. Okay, problem 7 is different. So it says we're taking the derivative of the dot product of two vectors. And you click on this little thing that says, hey, use this rule. And the rule is the derivative of the dot product of two vectors, number 4, says that just like product rule, you take the derivative of the first one dotted with the second one left alone, plus the first one left alone dotted with the derivative of the second one. So let's go back and look at that. So we need the derivative of both vector equations. So we have u of t is sine 5t, comma, cosine 4t, comma, t. And I can immediately find the derivative of this. So the derivative of sine is cosine, but this 5 is also going to come out front. So you're going to get 5 cosine of 5t. The derivative of cosine is minus sine, but that 4 is also going to come out front. So it's going to be minus 4 sine 4t. And then the derivative of t with respect to t is 1. So that's the derivative of ut. Okay, now let's do vt. V of t is equal to t cosine 4t, comma, sine 5t. So very, very similar. Therefore, the derivative is going to equal, derivative of t is 1. Derivative of cosine is minus sine, but the 4 will come out front, so minus 4 sine of 4t. Derivative of sine is cosine, but this 5 will also come out front. Oops, I forgot it. 5 cosine 5t. Using product rule there. 5 cosine 5t. Okay, so that equation said, let's see if color can really help us here. Take the derivative of the first dotted with the second left alone, plus take the first left alone dotted with the derivative of the second. And we're going to add those two results. So let's try violet. Violet's going to be, we're going to multiply u prime t with v of t. So we're going to multiply the first two terms together. We're going to multiply, oh shoot, I got that lined up wrong. We are going to multiply the first two terms. We're going to multiply the second two terms. We're going to multiply the third two terms. And we add them all together. So, u prime of t dotted with v of t is going to equal 5 cosine 5t times t, which is going to be 5t cosine 5t. Plus the second two terms, minus 4 sine 4t times cosine 4t. So the minus 4 is going to dominate. Minus 4 sine 4t times cosine of 4t. Plus the third two multiplied, 1 times sine 5t is just going to be sine 5t. Okay, now in red, we're going to do u dotted with v prime t. And I'm going to line these up so at the end we can just add down, because the idea is we're adding all this together. Okay, so I've got the first two, sine of 5t times 1. So that's going to give us sine of 5t. The second two are going to be cosine 4t with minus 4 sine 4t. So it's going to be minus 4 sine 4t cosine 4t. Then the last two are the third, which is t, with the third, which is 5 cosine t. So we're going to get plus 5t cosine 5t. And we are adding, boy, I'm running out of colors on this one. We are adding all these three terms together. Now you'll actually notice, hopefully, that this first term and this third term are the exact same. So when we add these two together, so I'm just going to put, adding those two equations, we're going to get 2 sine 5t's. And you might notice that this first term here, 5t cosine 5t, is the same as this one here, 5t cosine 5t. They're both plus, so we actually have 10 t's times cosine 5t's. And then the middle two terms are exactly the same. They're both minus 4, so those minus 4s will combine to minus 8, and you have sine 4t cosine 4t. And that is the answer. So I wrote a little different order. 10t cosine 5t is here. Minus 8 sine 4t cosine 4t is here. And 2 sine 5t is here. Okay, so hopefully the derivatives aren't bad and the dot product's not bad. It's just accounting. It's just keeping track of all these different numbers and letters. That's problem 7. Okay, 8's a pretty simple kind of guided problem, so this will be a nice little one for us to get a win. So it says, show that if the magnitude of the vector equation is equal to n, some constant, then the derivative of that vector equation is orthogonal to the original vector equation for all t. So they say, okay, let's find the magnitude of they say, let's take the dot product of these two vectors. So the dot product of these two vectors is the same as the magnitude of it squared, because you're basically taking each component times itself, which is the same as squaring individual components, adding them up, and then that would be the same as if I took the magnitude squared. But I know the magnitude is n, so this is just saying I'm squaring n, so some constant n squared. Okay, let's see this. And therefore n squared is a constant. So if n is a constant, squaring it will also produce a constant. So then it says formula 4 of this theorem, I think we just saw that one. Formula 4, yeah, it's the same one. If you take a derivative of a dot product, you take the derivative of the first dotted with the second left alone, plus the first left alone dotted with the derivative of the second. So we definitely just used that one. Then it says the derivative of RT dot RT should be R prime T dotted with RT left alone, plus RT left alone dotted with R prime T. But these are the exact same, and order doesn't matter in dot product. So this is the same as having 2 of the derivative function dotted with the original function. But here's the leap we have to make, is that we have to know that if R dot R is n squared, the derivative with respect to t of r, this is what they did not write here, I don't think very well, r dot r, which is this stuff. It's all this stuff here that they expanded out. But what is r dot r? R dot r is n squared. So the derivative of dt of n squared, so this says the derivative with respect to t of some constant, well, that has to be 0. So the derivative of any constant is 0, and n squared is a constant, so that's how they got that 0 right there. Okay, so then they can prove that the dot product of this derivative and its original function, that has to equal 0. Well, the only time you have a dot product equal to 0 is if those two vectors are perpendicular. So we just kind of proved that if the magnitude of RT is a constant, then the magnitude of its derivative has to be perpendicular. So not the magnitude. Then the derivative of the vector has to be orthogonal to the original vector. Okay, let's see. What else do we want? Okay, so that's problem 8. Okay, problem 9, determine whether the statement is true or false. The derivative of a vector function is obtained by differentiating each component function. So that's true. So that's what we've been doing since the start. We had if this is r of t equals some function t, g of t, h of t, then the derivative of this is just f prime of t, g prime of t, h prime of t. So that's how we did all those problems. So that is true. We took the components and took their derivatives. Okay, the last one says, if ut and vt are differentiable vector functions, then the derivative with respect to t of ut cross vt is equal to u prime t cross v prime t. Close, but not quite. If you click on that equation that we just looked at, the derivative of ut cross product vt is very, very similar. It's equal to u prime of t crossed with the original v of t, no derivative, plus leave u alone this time, crossed with the derivative of v. So it's just like product rule. You have to do 2 of them, and in one case, the first one gets the derivative. In the second case, the second one gets the derivative. So this one's false. You can't just say it's derivative of both crossed. Okay, and that will do it for section 13.2.